In this video, we will present some of the projects that have been conducted by Master 1 students in Control at ECAM during their Advanced Control on Embedded Systems Control Lab. This teaching activity is part of the Advanced Control 2 teaching unit and is supervised by my colleague Sébastien van Kouwenberg and by myself. Like last year, the students have been working on a mobile robot. They have either received the EduMIP mobile robot kit or the Balboa mobile robot kit. As you can see, the kit contains the mobile robot itself, a breadboard, some cables and wires, and ultrasonic and infrared distance sensors. If you want more information about those mobile robots, have a look at the video presenting last year's projects. This year we had 4 teams working on the EduMIP mobile robot and 4 teams working on the Balboa Pololu mobile robot. We'll present 4 out of the 8 projects, 2 involving the EduMIP robot and 2 involving the Balboa robot. We thank all students for their contributions and their willingness to let us present their hard work. Let us start with EduMIP Team 2, composed of Arnaud Dumortier and Fadim Rabet. They have taken up the light tracking robot problem. That is to say, the robot has to automatically drive towards a light source. As you will see, they have added a little twist so that the robot moves backward when the light comes from the back. As you can see, they have used 4 LDRs to achieve their goals, light dependent resistors, and this means that the resistance will change as a function of the light intensity. The 4 sensors are connected to the ADC of the BeagleBone Blue via a voltage divider circuit, and this voltage divider circuit will transform the change of resistance to a change of voltage. As you can see over here, the 4 LDRs are mounted on the breadboard and directed to the back, to the front, and to both sides of the EduMIP mobile robot. Using these 4 sensors, they were able to estimate the direction of the light source in the form of a so-called light angle. The meaning of this light angle is shown in this picture that shows the robot from above. Depending on the light angle, a light angle set point, a speed set point for the mobile robot, and the motion direction are set. The difference between the light angle and its set point is used to rotate the robot using a proportional controller. When this error is small enough, the robot is allowed to move forward or backwards depending on the direction of the light source. Let us now have a look at the test results with the music in the background selected by the students. Next, we'll have a look at the work of EduMIP Team 4, composed of Adrien Davidjuk and Yasmina too, and they have decided to take up the line following problem. To achieve their goals, they have decided to work with 5 infrared sensors. Such a sensor has an emitter side and a receiver side. The emitter side emits infrared light and the receiver side measures the light that is reflected back by the surface. A black line is characterized by the fact that it will of course reflect very little of the emitted light. They have decided to work with a very light wooden structure to attach the sensors to the robot in order not to affect too much the center of mass and the moment of inertia. In this way, they were able to keep the dynamics of the robot unchanged and to keep the performance of the controller that they had designed previously. This is the electrical scheme. As you can see, the 5 sensors are connected to available inputs on GPIO 1 and 3 to read the intensity of the reflected signal of each sensor. Each sensor is powered by a different 3.3 voltage supply and ground. The line following algorithm is implemented using a state machine with 4 states. These states are wide turn, sharp turn, straight line, and out of circuit. The software reads the signals coming from each sensor, and depending on the state, set points are sent to the robot control algorithm. Obviously, if only the middle sensor detects a line, the state of the state machine is straight line or go forward. In such a case, of course, the heading angle should remain constant and a relatively high speed set point can be set for the wheel. Let us have a look at the test results on a simple circuit and therefore fast, and a more complicated circle, therefore a little bit slower. Hamza El Makrini and Matthias Arbezu Granados are part of Team Balboa 3, and they've tackled the light tracking problem that we've seen before, but now for the Balboa robot. They have added a little twist in the sense that when the light comes from the back, the robot will turn 180 degrees. Balboa Team 4 will also use the LDRs or light dependent resistors that we have introduced before. In this case, they will just use 3 LDRs. 2 sensors are mounted on the front on both sides of the robot, and 1 sensor is mounted on the back. Well, when the light comes from the front, they will be able to detect the direction, so straight ahead or from the side. As shown in this scheme, the LDRs are connected to the robot using the same voltage divided circuit as introduced earlier. As you can see, the sensors are integrated in the protection hoops of the robot, and this leads to a very clean and neat implementation. A calibration or normalization phase allows the robot to adapt to the ambient conditions by compensating for the average light that it receives. As you will hear later in the video, the robot buzzer is used to signal the end of the normalization procedure. Based on the measurements, a robot state is determined and the corresponding set points are sent to the control algorithm. The states are do nothing. This is because the light can come from a blind spot. Go to the left, go to the right, make a 180-degree turn, and go straight forward. Let us have a look at the test results of Team Balboa 3. We will see 2 situations with very different ambient light conditions. And finally, we'll have a look at the work of Najim El Ayadi and Abdellah Belkacem. They are Team Balboa 4 and they will take up the line following challenge. They have added 2 elements of originality. The first one is that the robot is able to find the track, and the second one is that depending on the color of the track, the robot is given a special task. To meet the challenge, they have used the 5 QTR reflectance sensors that come with the Balboa robot, and they have added a color sensor. As you can see from the measurements over here, and the deviation of the first measurement with respect to the 4 other measurements, well, this first QTR reflectance sensor clearly detects the presence of black tape. This is how the color sensor is connected to the Arduino compatible control board, and the communication is via the I2C protocol. The measurement comes in the form of an RGB trip. In this way, it becomes very easy to detect the color of the track. So this is the track and the specifications that were chosen by Team Balboa 4. So the idea is to track the line and follow it, and to detect the colors and act accordingly. This is the algorithm of Team 4. So first detect the color. If it's red, stop 5 seconds. If it's green, exit the track. If it's blue, use the buzzer. And if it's black, you just follow the detection line algorithm. Let us now have a look at the detection line algorithm. There are 3 possibilities. If none of the sensors detect a line, then go forward because the robot has not yet found the track. If all the sensors detect a line, then the track has been found and the robot should be rotated by 90 degrees. Once on the track, the follow line algorithm is used, and this algorithm is used to keep the robot centered around the line using a controller. Let us now have a look at the final test results of Team Balboa 4. Thank you to all students for their hard work and for their willingness to share videos, slides and code. If you think this looks like a lot of fun, you're right, and you should join Team AU, the team of control engineers at ICAM. See you next year.